All right, welcome back to Fat Mama Physics. This is actually episode 8. Last one was episode 7. Messed up there. Of the topic D1 series. This video is a continuation of applying gravitational field and gravitational potential concepts with respect to graphs. Oh, and I do have a lovely graph here of the gravitational well between, I think it was the moon and a planet and its moon. And this type of question, especially with this type of graph, is a well-loved type question on IB exams. And I see it quite often in textbooks everywhere. I mean, not guarantee you're going to get one on your exam, but it's very necessary that we go over one of these together. This is the source of the question. You can probably find that on your own. But this is showing that here you have planet, which its surface is at point A. So from that, you can deduce the radius of that planet. And B is somewhere in between where the gravitational potential is at a maximum. And then point C is on the surface of the moon. So you can also deduce the size of the moon as well. And if you take a look at the shape of this graph, it's pretty characteristic of two point masses. You are trying to get out of the gravitational well of your planets, maybe planet Earth. And as you move further away, and then you get to a space around here, and then you get to another potential well, which is the moon. Question A is explain why the gravitational field strength at B is 0. So if we go to the definition of gravitational field with respect to gravitational potential, we know that it is the derivative or negative derivative of your gravitational potential, or the slope on a gravitational potential graph with respect to space. When the field is 0, it means that the gradient of the slope has to be 0. If we take a look at B, that is pretty close. You have a slope of relatively 0 here. So you can write that here. And by the way, you really need to pay attention to questions that say use the graph to do this. And it usually, IB questions like to state it here, to blah, blah, blah. Okay. So you need to really talk about the graph. So I'm lazy, I'm just going to write this down. You can do that yourself too. Okay, then question B is estimate the ratio of mass of the planet over the mass of the moon. And one of the things that IB questions are really good at is sometimes it kind of guides you through the thinking process. So in fact, if you see this question, you get stuck. Maybe the previous question might give you a hint of what you're supposed to do here. And this is really great for that. But even if you didn't use a previous question as a hint, you know that you have to find some sort of relationship between the planet and the moon. And one of those relationships is the fact that at point B, the gravitational field is 0 due to the relative distances, due to the distance between from the planet to the point B, from A to B versus from C to B. So I'm going to use that relationship, which G field due to planet at B is equal to the G field of the moon at point B. So for the planet, we have, to calculate gravitational field, this is big G, and this is going to be M. I'm going to use big M for the planet and small m for the moon. Over the radius, or not the radius, but the distance from its center to where point B is. So don't forget, A is just the surface of the planet, not the actual center of mass. So starting from 0 all the way to B, this looks like 6 times 10 to the power 7. Don't forget to square. And this is equal to big G small m, which we're talking about the moon, over that distance, again, from the center of mass of the moon to point B. C is also at the surface of the moon, so that doesn't count. This looks like from 8 to 6, that's about a difference of 2 times 10 to the power 7. Now we just need to do some cancellations and find the correct ratio. So it looks like we want mass of the planet on top and small m on the bottom. G's cancel out. So I'm going to multiply, or actually I'm going to divide the small m down to the other side of this equation. So we're going to get big M over small m because we're dividing both sides by m. And it also means I want to move the 6 times 7 to the power of 2 up to the top to the other side. So multiplying 6 times 7, all of this to the power 2, I get 6 times 10 to the power 7, all this squared divided by 2 times 10 to the power 7 in brackets squared. You could use a calculator, but you could do it without one. It's not that bad. So all you have to do is you just take this square and you apply this square to everything inside, right? Exponent rules from grade 9 math. 6 squared gives you 36. And then you have 10 to the power 7, all of this squared. I'm too lazy to do that because I know it's going to cancel out with whatever is on the bottom. 2 to the power of 2 we know is 4 times 10 to the power 7. All of this is squared and this lovely thing cancels out. We are left with now 36 over 4. That gives us 9. Okay, so on to C now. Use the graph. Hey, it says use the graph. So watch out for when they say use the graph because it's very specific. Use the graph to determine the gravitational field strength halfway between the planet and its moon. If we take a look at the planet and the moon, it goes from 0 all the way to 8. All the way to 8 because we're talking about the centers of these two masses. So half of 8 is 4, so that would be right here. This is where it might be useful to bring a ruler to your IB exam, or just have a ruler handy. Of course, we have them here in the classroom. So I need to make this space a little bit clear here, so I'm just going to get rid of that line that we used in question A, because what we need to do now is notice that to find the gravitational field strength on a gravitational potential versus distance graph, you need to find the slope, which means you need to find the instantaneous slope on this curve. So drawing that nice straight line is going to be very helpful. Okay, so this is the best that I've got, and yours might look a little bit different, but luckily on an IB marking scheme usually give you some flexibility. So after I draw my line graph, I pick 2 points on this line that I've drawn to find the slope. Try to make them as far away as possible, and of course if you choose the points on the grid lines, it makes your life a lot easier. So I'm going to cheat a little bit. I'm going to use that one, and I'm going to pick this one here, I think. Okay, I'm not... So at least the 2 points should be greater than half the length of the graph, ideally. So we know that slope is rise over run, or the change in gravitational potential over its space, over distance. So change in VG here, this is 3 boxes, which is 0.6, and this is increasing positive slope, so no need for the negative sign, joules per kilogram. Divided by the distance. So from 3 all the way to 8, that is total of 5, times 10 to the power of 7 meters. Put this in the graphing calculator. Did you spot a mistake I made? I couldn't see it because all my writing got in the way. So 0.6, ouch. 0.6 also times 10 to the power 7. Graphs are sneaky like that. So you also have to pay attention to all the units and all the scientific notations. So I get something along the lines of 0.12, and yes, this is technically joules per kilogram per meter, but we also know better that gravitational field is Newton per kilogram, or we also know is meters per second squared. But that is pretty good enough. Okay, and we got D and E, so now we have an object, a mass space probe. Oh, sorry, a space probe of mass, 2.4 times 10 to the power 3 kilograms is launched from the surface of the planet. Launched from A. Calculate the gravitational potential energy of space probe when it's at a distance of 1 times 10 to the power 7 from the center of the planet. So we don't need to worry about adding onto the radius of the planet because it's already referring to from the center of the planet. Because it's asking for gravitational potential energy, and it's not and the graph uses gravitational potential instead, we go back to the definition of gravitational potential energy. Gravitational potential energy is also the gravitational potential times the mass. And if we're just talking about a certain distance away from a planet, don't forget we're always comparing that relative to our reference point at infinity, which is 0 joules or 0 joules per kilogram. So we just take the reading from the graph, as of course the whole point of the question is reading graphs, 1 times 10 to the power 7, so that's right there, relative to the center of mass of A at 0. And just by reading this graph, I mean, I get the luxury of zooming in. Well, you may not, but I think based off of what is on your print, this is minus 1.8. And it could be more precise on my zooming, but I'm assuming you can't achieve that level of precision. So I'm just going to use negative 1.8 times 10 to the power of 7 joules per kilogram. And also times the mass of the space probe, which is 2.4 times 10 to the power of 3 kilograms. So I get, don't forget the negative sign, it will cost you points, minus 4.32 times 10 to the power of 10, which rounds to negative 4.3 times 10 to the power of 10 joules. Okay, and last question. Again, using this graph, determine the minimum work done that has to be done on the space probe so that it can reach the moon. We might be tempted, actually before we do this, surface of the moon so it can reach the moon, this is referring to C. We might be tempted to compare the gravitational potential between A and C and then find the difference, and that would be the minimum work done. But the problem with this is you not only need to get to C, but you also have to climb up this well, get to the top of the well before you can come back down. And so some of that work that you put into your space probe and shooting it away from this planet that you have may get converted to other forms of energy, but it is necessary to get you away from the gravitational influence of the Earth and at least to be where the gravitational field is 0. And once you get there, you can kind of you can then fall back down to C, which then some of that gravitational potential energy gets converted into kinetic. So yes, by definition, it seems taking the difference between A and C seems like the logical answer, but don't forget in the actual situation, the space probe has to get out of that well, get out of that potential well. So the work done is then, of course, change in the energy, specifically the potential energy in this case. To find that, we find the delta, the change in gravitational potential times the mass. So by definition of what the gravitational potential energy is. Gravitational potential then, or the difference between gravitational potential, we'll need to compare the gravitational potential at B versus that at A, because it has to leave the well. What we have is minus 0.4 times 10 to the power of 7 minus, all of this in big brackets, minus negative 4.4, which is at A, negative 4.4. Reading graphs is very important, times 10 to the power of 7. And all of this times the mass of the space probe, which is 2.4 times 10 to the power of 3. And then after putting all this in the calculator, we're going to get a positive number because this becomes plus. Minus and minus gives you plus. I get 9.6 times 10 to the power of 10 joules. There you go. Otherwise, that's it for examples in applying the gravitational field equation in respect to gravitational potential. Hopefully this graph gave you some practice. I encourage you to try more of these graph questions. Practice, practice, practice. There might be one on the test. Anyhow, wish you good luck. Fat Mama Physics, signing out.